Okay, we've been talking about crystal structure quite a bit lately, and you may wonder, why are we doing that? What's the point? Maybe we can calculate theoretical density. That's perhaps interesting. I mean, I hope it is. But is there more to it? And yeah, there is. There's certainly a lot more to it. There's so many things that we can explain and properties we can control with knowledge of crystal structure. So I want to give you a few examples that can just sort of give you a little taste of some of the stuff that you can apply this knowledge to. So first of all, I'd like to take a look at an arrangement of atoms. Here's an arrangement of atoms in 2 dimensions. There's something special about this. This is what we call a close packed plane. You could not pack circles into an area more efficiently than this. To contrast with that, this arrangement of atoms, you might appreciate, is not close packed. If I look like this, you can see more of my face through this arrangement of atoms here than you can through this one. This obscures more of it. More of the area is covered with atoms or with circles in this case than it is in this. So if we take these close packed planes, this is one way of looking at a structure, we can take close packed planes, and it turns out if you stack up close packed planes, there's a certain way to do it. You can form face-centered cubic. Okay, and face-centered cubic is really neat because it actually has a lot of these little close packed planes that are available for deformation. And when you plastically deform a metal, what happens is the atoms slide past each other like this. Okay, along close packed planes. There's one extra level of detail to the mechanism that's not captured here, but we'll get to that later. But the general gist of it is they slide past each other like this. Okay, over here. Oh, look at that. Isn't that gorgeous? These little close packed planes are sliding past each other. Okay, that's plastic deformation. So let me show you a couple of other little models. And so if you look at this arrangement of atoms, you might recognize that as something. What do you think? Front face of FCC, front face of FCC. Absolutely. So when you look at that, and then I'm going to show you another arrangement of atoms here. And there we go. So what about that one? Does that look familiar? You might think simple cubic. Take a look at this. There's face-centered cubic. You confirm the front face of an FCC unit cell. Now watch when I rotate this 45 degrees. Look at that. They're identical. These are exactly the same plane. It's just this one I had this box machined so that the conventional face-centered cubic face was visible, whereas this one, it's not. The close packed directions, the directions where the atoms are touching, are parallel to the sides of the box. But these are exactly the same base, and we can actually build the same structure from them. So if I add some atoms to this one, you will recognize the conventional face-centered cubic unit cell starting to form. Okay, if you look at the sides there, you can start to see that. I think you'll be able to see the 1, 2, 3, 4 corners and the one in the center, right? That is face-centered cubic. So this structure here is face-centered cubic. You're all experts on this structure by this point. So that's face-centered cubic. Now let me show you face-centered cubic another way. This is going to be a face-centered cubic. Trust me, it is. And this is another way of building face-centered cubic, but I'm going to build it a special way where the edges taper back. And we do that for a reason, it's going to show us something really interesting. Look at that. Now, what's that face, that triangular face that's looking at you right now? Take a look. What is that? Look, in fact, there's 4 of them. Okay? What's special about that? What's special about, sorry, bring it back into focus. What's special about those 4 triangular faces that you can see there? Well, those are close packed planes. It's the same arrangement as this one. And I said face-centered atoms, face-centered cubic materials have, well, now we know they've got 4 of those close packed planes that are not parallel to each other, and so there's many opportunities for atoms to slide and plastically deform extensively, like this, like I'm demonstrating here. So that's a really exciting thing about face-centered cubic materials. And in fact, I'll take you over for a little walk in my office here. You might notice up on my shelf, I've got some aluminum beverage containers, okay? And this is a fascinating example of the application of a face-centered cubic material. Let me get this one down, I'll get this one, and that one down, okay? And then let's come back over here and talk about that. It's really, really neat. Aluminum beverage container starts off as a thin, flat little piece of aluminum, and then it's punched to form this little cup, okay? And then they go through a series of other deformation operations to stretch it out to this height. It's a huge amount of plastic deformation. Really, really fascinating. But the only way this is possible with the ease at which, and it's complicated, but the ease at which they can do it is because aluminum is face-centered cubic. And so there's all these nice little close-packed planes. When this can's being stretched out, that can slide past each other. You can make beverage containers similar to this out of BCC steel, but it's a little more challenging to do it and difficult to get as thin, if even possible. So face center cubics materials are great examples of this in your kitchen sink at home, perhaps. If you have a stainless steel kitchen sink, it will be face center cubic. Try sticking a magnet to it. Another consequence of it being face center cubic is it's non-magnetic, even though it's iron. But it's made from face center cubic stainless steel, austenitic stainless steel, because there's all those close packed planes that can slide nicely. Okay, let's take another look. Here's a little unit cell, and iron, like I said, is BCC at room temperature. And let's say we had a crystal, a single crystal of iron. And I wanted to compare the Young's modulus along this diagonal direction versus the one of these edges, like this, along this edge direction, like that. Okay, could we predict the Young's modulus in these two scenarios? What do you think? And I'd like to show you that, in fact, with what we've discussed so far, we can predict that. So let me get you a little hint here. You remember we discussed the interatomic force separation curve. Okay, and we said, well, the interatomic force separation curve looks something like this. Right? Peak like that. And we were particularly interested in this point right here, the slope at r equal to r naught, the equilibrium interatomic spacing. That was df by dr, you'll remember, at r equal to r naught. And we said that's directly proportional to the Young's modulus. So now we can say, well, which direction in this cube are the atoms touching? Well, for BCC, they touch across the cube diagonal. In fact, I've got a BCC unit cell here. It's going to be difficult, perhaps, to see the cube diagonal, but it's going on this angle. That's the front face of a conventional BCC unit cell, and you might be able to see the direction that they touch. And you can also see very clearly that they do not touch across the edge. There's a space there, right? So that means along this edge, they're spaced out further. The equilibrium interatomic spacing is further to the right, okay? So what happens to the slope as you go to the right? It decreases. So the Young's modulus, we would expect, just with this simple little discussion, to be less along the edge than it is along the cube diagonal. And that is, in fact, correct. Along the edge, it's around 125 gigapascals, and along the diagonal, it is 273 gigapascals. So huge difference, and we can explain it with some knowledge of crystal structure. Okay, let me give you another example. You're watching this right now thanks to some semiconductors in the computer or a smartphone or whatever it is that you're watching this on. And here's a silicon single crystal. Isn't that gorgeous? Look, so this is a single crystal. This is atomically smooth. So these single crystals of silicon are the basis for semiconductor devices and all these in all your computing devices. So a vat of molten silicon, an extremely clean environment, is seeded with this little seed crystal with the correct crystallographic orientation, okay, and then that's withdrawn, and this great big long like sausage is formed, which is just a single crystal of silicon, and then they're sliced up, and just like we said here that the mechanical properties of iron would be different along the edge and the diagonal direction. Similarly, the electrical properties of these semiconductors are different in different crystallographic directions. So it's really important that we understand that. And it turns out that this face here that you're looking at, it's atomically smooth, is it's actually similar to one of these planes here. The structure of this silicon is the diamond cubic structure we'll cover later in the course. But it's really the same kind of plane here that we've seen in face center cubic. Okay, so that's what you're looking at right there. Atomically smooth, beautiful. So let's see if we can apply some of this knowledge that we've got to another example. And that example is going to be the behavior of a ceramic versus the behavior of a metal. Okay, so we're going to look at a metal, versus a ceramic? Could we rationalize some of the behavior? Well, just with the little discussion right now we've had with these planes sliding past each other, we said, well, we know that planes of an atom, of a metal rather, must be able to slide past each other. In fact, that's true. So if I simplify it a little bit here, I go do something like this. We apply a force to these planes, you will find that they can slide past each other. And the result is you're going to have, and we will discuss this mechanism, the specific mechanism, in more detail later in the course. But for now, the end result is that they will be able to move like that. And that is, of course, what we would call plastic deformation. But why is it then that a ceramic cannot? And could we explain that behavior with the knowledge that we have of, say, the rock salt crystal structure? And I am here to tell you, yes, we can. Oh, it's gorgeous. It's good stuff. This is exciting. I mean, look at this. So here is the structure that you know to be accurate for rock salt, right? That is the crystal structure for rock salt. That's an accurate two-dimensional slice through it. So now what we want to do is we want to say, well, what's going to happen if we apply a force to this crystal here? Okay, what's going to happen? Well, there's an interesting scenario that occurs that is not the case for a metal. What happens is you end up, to get those to slide past each other, you have this scenario here that is an intermediate scenario where you've got, and I'll remind you of the charge here, right? We've got these little cations are positive in charge, okay? Positive in charge. And we'll cover the charge and the electron configuration, the type of bond in more detail later. But they've got a charge, and we get this intermediate scenario where like charges come very close to each other. And so what happens? Instead of plastic deformation, you get brittle fracture because the charge repulsion prevents the planes from sliding nicely past each other. Okay, so that's just a few little examples of some of the application of crystal structure. It's so much more diverse than that, but I just wanted to give you a little taste of it. Okay, I hope that was interesting for you. Thank you.